So we can take advantage of that. And here's how. Here's our box. We can use a thing called tet conform. Tet conform will convert this into tetrahedrons. These tetrahedrons are usually used for finite element method solves, which is used for like squishy squids and other things. You know, volumetric simulations, volumetric geometry simulations. Again, usually squishy, rubbery things. Vellum, in general, uses tetrahedron things. So you could configure tetrahedral soft bodies, where we break up a pig head, again, into tetrahedrons or something like that. So here we go. We look at it. There's just a whole bunch of, you can see them on the inside there, can't you? Whee! There's all these different tetrahedrons everywhere. I just want to use it on this box. So the box is now 12, where each one is essentially one of the outside triangles. And then it looks like, so 1 point, 2 point, 3 points, and then this fourth point in the middle. So each one of these triangles is getting that treatment. So again, so now anywhere inside this box can be defined in terms of which tetrahedron it's in and where in that tetrahedron it is. So the beauty of this is that now if we move, so consider this the rest geometry, and this is the deformed geometry, I can look up any space in this deformed tetrahedron, and it'll say you are in tetrahedron 8, you are at this tetrahedron coordinate within it, and then I can look up where that is in world space in the before it's deformed, because it's still the same amount of tetrahedrons, and there still is a point in space that is in that same relative space inside of that tetrahedron. Different world spaces from here to here, but that's what I want. I want to basically go through this with a volume wrangler and say at any given voxel, where am I inside the tetrahedron, and then look up what density was there in that tetrahedron before it got moved. So I hope that that makes sense. But like I said before, you're in volume 6, baby. So things were going to get complicated, and perhaps, as is often the case, it will make sense as we do it. So we're already halfway there anyway. So first things first, we need to make a new volume. You know, when I moved this here, we're now outside of where the volume was originally. So here we are with our old volume. When we did our twist, you know, we were able to take advantage of the fact that we were going to put density into areas more or less where they already were. And of course, we had to account for it a little bit with our activate, but more or less. Now that we might be doing a much more drastic deformation, we need to make sure that our new volume encompasses everywhere where it might go to. So we need to make a volume, a new volume, a brand new volume, starting from this. So I'm going to use a regular Houdini volume for now. We could convert this to a VDB later. I'm going to use a Houdini one because I don't want to worry about things being active or not active or anything like that. I just want to have a fully dense, memory inefficient, but not going to make any mistakes and, you know, good time. So here we are. Let's do by size. I'm going to say, let's have it be a pretty coarse volume, 0.2. So we can see it already does have the dimensions of basically a box around this. So you can see it now. So this box is the dimension that encompasses this. See that? So this volume doesn't show anything yet because obviously there's nothing in it, but it does exist and it does have voxels that are a size 0.2. So there's our volume. That is the volume that we're going to do our volume wrangle on, this empty volume. It's going to draw from this here, but it's starting from nothing. But it's bigger now, as we've just said. So I'm going to say, let's actually also name this while we're here, density volume. What are you complaining about? Good, nothing. So we want a density volume. We're actually also going to want a temperature volume, so we might as well just do that now. So if we middle click and hold, oh, told. I thought I could do both at once like that. I guess I'll just do a one of these that we've gotten so used to doing now. Temperature, merge, boom, 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 boom. So now we have density and temperature. I actually want I want density to come first because I think that's what we were doing over here. Makes me feel better. So here we are. Here's our Wrangler. And now we're going to get to it. So everything we just said is what we're going to implement now, which is we're going to look up where we are in space as we iterate over each voxel, like where we are in terms of the tetrahedron, like which one we're in and where we are inside of it, and then simply look up in the original non-deformed version where that is in the world, and then we'll look up where that is in the world in the original volume. So without further ado, here we go. Let's define some things. Prim number will be which of the tetrahedrons we're in. Vector UV will be not UVs the way you're thinking of, or perhaps you're thinking of, but this will be that alternate coordinate system that defines where we are in that tetrahedron. So U, V, and W more accurately than U and V. Vector, of course, is actually a 3 valued thing. In fact, I'll just call it UVW. There are 4 points in a tetrahedron, but the last point can be implied. All we really need is the 3 measurements of the first one, and the 4th one must just be the remainder. So UVW. So first things first, there's this wonderful vex function called XYZ dist. XYZ fist. Oh god, that's something else. XYZ dist. And we're going to say look into this incoming geometry stream, which I'm going to say is 1. So that's going to be this deformed one. So again, we have the static, the deformed. So look in the deformed one. So that's input 1. That's why this is 1. And look in, of course, at our current location. And this is unusual for vex kind of stuff, but I want this to store which primitive we are in this variable here, and store what the UVW is here. You're probably much more used to having like the result equals this. That's not how this one works for reasons that are, again, are kind of outside the scope of this, except to say that this is a way that we can return 2 different values. We're returning which primitive we're in and also what the UVW is. Normally when we get return values from functions, we're only getting 1 value. As it happens, we actually do receive a return value from this. It's the distance we are to that primitive. In this case, we're not going to use that value, but just so you know, it is returning this value, but I'm not going to use it. So at this point, it looks like we only received this dist, but it actually has set the primitive variable to the primitive here. And again, this. So these are now both set. So immediately on the next line, I can say, well, how about you tell me where in world space that is? There's a complementary function to this XYZ dist, and it's called prim UV. I mean, really prim UVW for us, but it's just called prim UV. So tell us, if I were to say, look right back in input 1, we are going to change this, but for now, humor me. P position based on the prim and UV. W. So what this is saying is look in this geometry stream and say at this primitive, at this UVW, which is what we just got, tell me what is the P attribute. You could choose other attributes, but I want the position. So by doing this, we're simply going to receive ourself. We're going to receive the original P, because this said at the position, give me the tet and UVW, and now this is saying, given the tet and UVW, give me the position. So it's just going to return P. So that's not useful. Instead, I want to say, don't look it up, though, in our deformed universe. Look it up in the original universe, the original frame where we didn't have it be deformed. So what is represented by the undeformed or the non-deformed thing? So change this to 2, because we're looking at that one. So that's pretty much it for that. And so now we have the original world space position. Now, it still doesn't tell us what the density is. For that, we now simply have to ask for the density from the volume itself. So for that, I can just put this in here. This is when we had just the regular untwisted volume. And I can just say the density then, in our new empty volume, at least for now, is going to be volume sample. So this is the same as before, at least. The third input, the density volume, and at the world space location we just determined. And that is it. And voila! It worked. So now all you can do is you can move this point around, and you can see it's deforming it. It's doing it quite fast. And again, unlike a lot of more problematic implementations of volume deformers I've seen, this one will never run into an issue of stretching. We can stretch this forever. It'll always work. We might run out of memory because our volume's getting bigger and bigger, but that's something that's a general limitation of volumes. But that's the point. So now I can do all kinds of crazy stuff. I could select all these points. I can move them all up. I could do something like, this is breaking because this has now popped out. Say, the tetrahedron became inverted. So make sure that that doesn't happen. See how it's on the inside? These tetrahedrons are nicely formed. Once one tetrahedron is now passing through like that, some of them are getting inverted. So that's just going to be a limitation of this, but it's not a real limitation. If I wanted to, let's say, move this whole thing over like this, I could do like a soft radius. Let's say, here we go. Something like that. So basically 30. I already know this thing is 30 units tall, remember, here. So I can basically move this like this. So now I'm just skewing the volume without issue. And that thing on the inside is never going to pop out. Yeah, you could do a lot with this. Popping out if I do rotation, though. You can do quite a bit with this. We could make more tetrahedrons if you need more resolution, which we actually are going to do. But that's the general idea of this. If I were to take this box, I could have more divisions, like so, which is going to make more tetrahedrons in the same manner that we saw before. The particular strength of this method that I'm showing you here is that we are not going to use an edit to actually drive this deformation. We're going to use procedural things to drive the deformation of our mesh here, our skeleton, and then that will drive the actual, the final thing. Meaning, here I am arbitrarily moving these points, but we're actually going to use these points. We're going to move these points in a more procedural manner in just a moment. But in the meantime, it's cool to see we now have our animation flowing through this deformation. So once again, we have a cool looking simulated thing without doing any simulated work. We could even jump ahead and say, spoiler alert, we actually don't really need this VDB activate anymore, because now that we're using a dense grid here, everything's activated everywhere, and it's also not a VDB. So just so you know, we don't need that anymore. But look here, now we're doing a twist on that crazy thing. So it all works together still. And you can make pretty weird effects. But anyway, we're not going to do that. Let's move on to what we're actually going to do.